In this video, we will learn how to determine the polarity of molecules. So to determine whether a molecule is polar or nonpolar. The first step in the process is to determine whether the molecule has a polar bond to begin with. And that depends on the electronegativity of the elements. Electronegativity is defined as the ability of an atom in a bond to attract shared electrons toward itself. And basically it means if two atoms come together to form a bond, which of those atoms wants the electrons more? And the one that wants electrons more is going to pull them toward itself rather than sharing those electrons equally. So what you're going to do is look at the electronegativity chart, and here the higher number on the chart means that the atom is more electronegative, which means it wants electrons more. And if we take a look at the chart, we'll find that fluorine is the most electronegative element on the periodic table. It has an electronegativity of 3.98, which means it really, really wants electrons. And you can compare that to alkali metals, for instance. We see that francium has an electronegativity only of 0.7, which means it really doesn't want electrons. And that kind of makes sense if you think about the fact that alkali metals lose electrons and halogens tend to gain electrons in order to fulfill their octet. Okay, so you're going to look at the electronegativity differences between two different atoms, and that will tell you whether that bond is polar or nonpolar. So you're going to calculate those differences. If that electronegativity difference is between 0 and 0.4, that would be a nonpolar covalent bond, which means that the electrons are being shared equally. And what this means is that, let's say we had a hypothetical atom A and atom B, and those came together and they shared electrons to form a bond. Here, the electrons are being shared equally, so neither side is pulling the electrons toward itself more than the other. They are being distributed more or less the same way across the two atoms. If the electronegativity difference is between 0.5 to 1.8, then that would be a polar covalent bond. And here the electrons are being shared still, but they're not being shared equally. One atom is going to pull electrons toward itself more than the other. And let's say hypothetically that atom B was the more electronegative one, it means it will be pulling that electron density toward itself. And these electrons are going to be much closer to B than they would be to A. And because of that, B is going to have a partial negative charge and A will have a partial positive charge. And this means that there's more electron density around B. And since electrons are negative, this is a partial negative charge. Partial because they're still sharing electrons. B didn't completely take them, but it's pulling those shared electrons toward itself. That is what we call a dipole. And sometimes it's expressed by these partial charges. Sometimes it's expressed with an arrow pointing toward the more electronegative atom, and then a little plus sign on one side of the arrow to indicate the side that has fewer or less electron density. If that electronegativity difference was really large, so 1.9 or greater, then that would be an ionic bond. And in an ionic bond, electrons are not even shared anymore. So electrons not shared, electrons are transferred from one atom to another. So from less electronegative atom to the more electronegative atom. And let's say hypothetically that B was way more electronegative than A. What would happen is that B would take that electron from A, and when that happens, keep in mind that electrons are negative, so B would become negatively charged and A would become positively charged because it's negative particle left. In that case, we would have an ionic bond, and in ionic bonds, electrons are not shared anymore. They have been completely transferred from one atom to another. So that's really the first step of figuring out whether a molecule is polar or nonpolar. we need to determine whether it has a polar bond to begin with. And the way that you're going to do that is by, well, subtracting the two values and seeing whether there is an electronegativity difference large enough to give you any kind of polarity. So let's try a few of these. I'm just going to copy that chart to the next page to make things a little easier. Okay, let's try HBr, for example. So if we have a bond between hydrogen and bromine, what you're going to do is find the electronegativity of hydrogen, which is just listed on the periodic table, and the electronegativity of bromine, which is 2.96. And then you're going to subtract those two values. I always subtract the smaller one from the larger one just so that I get a positive number. If you did this in reverse, that would be totally fine. Just take an absolute value to make it a positive number. I see that electronegativity difference is 0.76, which falls into the polar covalent category. So that would be a polar covalent bond. And that means that the electrons are not being shared equally. So in that bond, we need to determine, well, which atom wants those electrons more? And looking at these values, I see that bromine has a higher electronegativity value, which means it's pulling that electron density toward itself. So you could draw a dipole going in the direction of bromine, or alternatively, you could put a partial negative charge on bromine and a partial positive on hydrogen. One thing to watch out for is that this is an electronegativity chart specifically, and sometimes students mix this up with the periodic table. So just be very, very careful. These are not molar masses. They're not telling you the mass of a particular atom. All they're telling you is how much an atom wants electrons, and these are all very small numbers, whereas molar masses can get really large. If you see something in the hundreds, it is definitely not an electronegativity value. So just watch out for what type of chart you're referencing. Let's try another one. And here is why, for example, a carbon-carbon bond will always be nonpolar. And this is kind of intuitive in a way because it's just an atom bonded to itself, which means that it wants electrons the same amount. But if you're not sure, you can always do the subtraction, and well, carbon has an electronegativity of 2.55. The other carbon also has an electronegativity of 2.55, so that electronegativity difference is 0, which means that these carbons would share electrons completely equally. There are no partial positive or partial negative charges here. Let's try another one. Okay, so let's say we want to determine whether a carbon-oxygen bond is polar or nonpolar. Carbon has an electronegativity of 2.55, as we determined in the previous example, and oxygen is 3.44. So all we're going to do is subtract those two numbers and see what they give us. And that is a value of 0.89, which on the chart is telling us that is a polar covalent bond. And since oxygen has a higher electronegativity value, it means it is pulling electron density toward itself, and the dipole is going toward oxygen. Let's try NaBr. Na is sodium, and it has an electronegativity of 0.93. Br is bromine, and it has an electronegativity of 2.96. I'm going to subtract those two values. And I'm getting 2.03, which is really huge. And notice that this is in the ionic territory. So this electronegativity difference is so large that these electrons are not even shared anymore. That is an ionic bond. And here, bromine completely took the electron from sodium. So that electron is entirely transferred to bromine to make bromide, the ion, and a sodium cation. And finally, let's try one more. Okay. Here we have carbon, which we previously determined had an electronegativity of 2.55. Nitrogen is 3.04. And I'm going to subtract those two. And I'm getting 0.49. Now notice this is actually can be a little bit tricky because it's somewhere in between these two values. And here you're just going to use standard mathematical rounding. 0.49 would round to 0.5. So that would be a polar covalent bond. So whenever you're kind of in between, just use the normal mathematical rounding rules. Okay. That is step one of determining whether a molecule is polar or nonpolar. First, you have to determine whether there is a polar bond in the first place. If there is no polar bond, then the molecule is nonpolar. And if that's the case, you don't have to think about it any further. So for example, let's say that we had CH4. That is methane. The only kind of bonds that we have there are carbon-hydrogen bonds. And what you would do is calculate the electronegativity differences between carbon and hydrogen. So you would subtract those two values just like we did with everything else, and you would find that this is a nonpolar covalent bond. If there is no polar bond, the molecule is nonpolar. And there is no need to think about it any further than that. Completely nonpolar, you are done. You don't need the shape of the molecule, you don't need anything else. Where things get a little bit trickier is if you have a polar bond. Because if you have a polar bond in a molecule, that does not necessarily mean that the entire molecule is polar. Then we have to think about it further. So let's look at an example of that. Let's say that we had CO2, for instance. I know that I'm going to have carbon-oxygen bonds here, and previously we calculated that, and we determined that the carbon-oxygen bond is polar covalent. So we definitely have a polar bond. And if we have a polar bond, so if there is a polar bond in the molecule, then we have to think about this further. And then you have to determine the shape of the molecule. So we're looking at molecular shape, not electronic shape. You will need to draw the dipoles and determine whether the dipoles cancel. So do the dipoles cancel? If they do cancel, then the molecule is nonpolar. If the dipoles do not cancel, then the molecule is polar. And that's where a lot of trouble happens, because sometimes students will see, okay, well, I have a polar bond, polar molecule. But it's not that simple. If you have a polar bond, that does not necessarily mean that the whole molecule is polar. So let's look at our CO2 example. I'm going to draw the carbon dioxide shape and the Lewis structure. So if you're not familiar with drawing that, make sure you review the Lewis structure video so that you know how we got to the CO2 structure. So that is the Lewis structure of the molecule. The next thing we have to do is figure out the shape of the molecule. And for that, watching the Determining the Shapes of Molecules video will be helpful. I'm going to look at the central atom, carbon. Notice that there are 2 electron groups around carbon. So remember that each double bond counts as 1 electron group. So here we have 2 electron groups, which means it has an electronic linear shape, and there are no lone pairs of electrons on the central atom, so this would be a linear molecule, which means that the Lewis structure and the shape of the molecule is actually exactly the same. The next thing we have to do is draw the dipoles. And when we calculated the electronegativity differences, we found that oxygen is more electronegative, and it's pulling that electronegativity or the electron density toward itself. So we drew the dipole pointing toward oxygen, which means there's a dipole here going toward oxygen. There's also another dipole going in the opposite direction toward the other oxygen. Notice you have two forces that are going in equal and opposite directions, which means they cancel. So here the dipoles cancel, and the molecule overall is nonpolar. And that may be a little counterintuitive, right? Because you had a polar bond, it's very tempting to say, okay, polar bond, polar molecule, but it's not, because these dipoles cancel. So that may be possibly the trickiest part of this whole deal. Okay, let's try another one. In the previous videos, we drew the Lewis structure of ammonia, and it looked like that. And then we determined the molecular and electronic shape of ammonia. So I'm going to go through this pretty quickly. You can check out the previous videos if you forgot how to do that. So focusing on the nitrogen, there are 4 electron groups around it, which means that the electronic geometry is tetrahedral. But keep in mind that for molecular geometry, we are only concerned with how the atoms connect. And if there is a lone pair of electrons on the central atom, which there is, then the molecular shape will be trigonal pyramidal. And based on that, ammonia is going to look like the following. Okay. And really what I should have done here first is to calculate whether there is a polar bond to begin with. I kind of got ahead of myself there. But we will find that when we calculate that there is a polar bond. So I forget the electronegativity of nitrogen, 3.04. Okay, nitrogen is 3.04, hydrogen is 2.2. So I'm going to subtract those two values. And I'm getting 0.84, which is a polar covalent bond. Okay, so that's why I instinctively drew the Lewis structure and the shape, because I knew that this was going to be a polar bond. But that would be the first thing you would do, see if the bond is polar to begin with. Okay, looks like nitrogen is more electronegative, which means that the dipoles are going toward nitrogen on each of these bonds. And it doesn't actually matter which direction the bond is going in terms of whether these dipoles cancel or not. But notice that here, the dipoles do not cancel because we have 3 dipoles going in the same direction, but then there's nothing up here. There is no dipole up top to cancel out the remaining 3. So the way you can think about this is that in order for the dipoles to cancel, the molecule has to be completely symmetric. So I would need to have another NH bond up top in order for these to cancel, and I don't. That's just a lone pair of electrons. So here dipoles do not cancel, which means this is a polar molecule. And this is a case where you have a polar bond and a polar molecule. Sometimes it works out that way. Sometimes these things cancel out and you end up with a nonpolar molecule. Let's try another one. Okay, so here you have a scenario where you actually have 2 different types of bonds. There's a carbon-hydrogen bond and a carbon-chlorine bond. And if you're ever not sure, you can just draw the molecule and prove to yourself that is the case. So I'm going to go through and calculate the electronegativity differences, and you're going to have to do this separately for each bond. So carbon, we said, I believe was 2.55. Yep. Okay. Carbon was 2.55, hydrogen is 2.20, which means our electronegativity difference is 0.35. So that is a nonpolar covalent bond, which means right now it looks like that could potentially be a nonpolar molecule, but we have to check. We have to check the other bond that is present here. So we'll take a look at the electronegativity of chlorine. That is 3.16. Went too far. Okay. And I'm going to subtract those two values. And that is giving me a value of 0.61. That is a polar covalent bond. And as soon as you have a polar bond, you have the potential to have a polar molecule. So here I have to draw the shape of the molecule, which means the first thing I have to do is draw the Lewis structure. We did draw the Lewis structure in the previous video, so do check that out if you are not sure. Okay. For determining the shape of the molecule, I'm going to count the electron groups around the central atom, and there are 4 of them. So 4 electron groups means you have tetrahedral geometry for the electronic shape. Now, because the central atom does not have any lone pairs of electrons, the molecule geometry is the same. So the molecule shape here is tetrahedral. And again, don't let the lone pairs on chlorines deceive you. We're only interested in the lone pairs on the central atom, which is carbon. If I draw the molecule shape, it will look like that. And then I need to draw the dipoles on the structure. Based on the electronegativity values, chlorine is definitely more electronegative than carbon, which means chlorine is going to be pulling electron density toward itself in all of these bonds. So we have 3 dipoles pointing down, but notice that the top bond is nonpolar covalent, which means you don't have a dipole up top. So there is nothing up top to counteract these 3 dipoles that are pointing down. So here the dipoles do not cancel. And since they don't cancel, the molecule is polar. Okay, so this skill set is going to be very critical for determining the intermolecular forces that a particular molecule has, and that will be the next video.